In the previous video on the moving coil galvanometer, we had already discussed the concept or the principle of working of the moving coil galvanometer, which works on the principle of the torque acting on a rectangular loop which carries current in placed in a uniform magnetic field, as we see on our screen. Then with the formula available for the working, we must consider the construction uh, which leads to the uh, proper working of the moving coil galvanometer. Now it's the case where we had obtained, so we are officially going to discuss the exact form of the moving coil galvanometer in this case. So let me write that down. Moving coil galvanometer, I'll be using the short of it, that is MCG. Now the construction involves, it has a different approach to it in case of the magnetic coils or the permanent magnets that are used. Now if we see over here, we have a two-dimensional view of it. If we see over here, what we have used is the North Pole and the South Pole, which is placed, this is the South Pole and the North Pole, and they are just rectangular blocks that have been used, but that won't really help because we are ending with a factor of cos theta right down there. Over there, as you can see, we are ending with a factor cos theta, and as the coil twists uh, while the torque acts, the value of theta changes, and we do not want that because that results in the value of the torque changing every time. Won't really give us a good result. So in order to obtain a better result, what we do is we consider we take the um, cylindrical magnetic poles into consideration. The cylindrical will be again using the front on view and the top view for discussing the entire thing properly. So first up, we have the front on view, just as the previous diagram that I was showing you. So that's more or less the case where we are using, I've tried to construct the three-dimensional view for you, where we have the North Pole. As you can see, it's not a flat surface, it's more of a curved one. Same is the case with the South Pole, and these are cylindrical poles. And the wire that you see, the rectangular frame that you see, multiple number of turns, one over the other, with the current entering and the current leaving, that cannot just hang there just like that with that rectangular frame. It has to be wound over something, so we use somewhat a cylindrical core. So this is what we use. We construct a cylindrical core, a soft iron core, cylindrical soft iron core, over which it is wound as a support. And this core, what happens to it is that it hangs from a certain point, and so that it's free to rotate about that axis from which it hangs, and while the magnetic field does the work of the formation of coupling force on both the arms that we just studied in the previous video. Now this can have we can have a top view of it. The top view will be much more pleasing, I would say, where we have the North Pole, the curved surface of the North Pole, and the South Pole over here, and the cylindrical core from the top view looks like this, and over it maybe at a certain instantaneous angle, the wires which are wound, and they carry the current with it. They come outside, come to the top from one side, and they are aligned along the field lines, and then they go down. What happens over here? What's the idea behind this kind of an arrangement? How does it help us? Well, it what it does is that the field lines, as you know, the field lines act normal to the surface of the poles. So here in this case, right from this point, one of the lines of force that I'm indicating, the magnetic lines of force, that comes out like this and goes to the south pole. What about any other point? Let's consider this point. At this point, what happens is that it comes out like this, being normal to the surface of that curved, being normal to that curved surface that we have for the North Pole, and it enters the South Pole similarly at right angles. Similarly, at any other given point, what it will have is that it will come out normally from that surface, and it will enter the South Pole normally as well. So all that we see is that at every point, with the lines of force being normal to the surface of the North Pole as well as the South Pole, the cylindrical surfaces, we are getting a radial field. So that's the idea behind this. We'll be achieving a radial magnetic field. And with a radial magnetic field acting, if the coil rotates through a certain angle under the influence of the coupling force, the lines of force, some of the lines of force at least, are always aligned to the flow of current on that top surface. If you observe the flow of current on the top surface, then what we have is they go like this along that direction by the red lines that I have marked, red arrows, and any of the given lines of force at any given instant of time will always be aligned with it. And as a result of which, the theta component that we were getting in the expression for the torque, now the expression for the torque is tau is equal to NIAB cos theta, or sine alpha maybe, but here we are concerned about the theta. So with that angle, with that wire being aligned to one of the lines of force, the angle theta is reduced to 0. So with radial field lines, what we get is theta gets reduced to 0 degrees, and as a result of that, cos theta goes to 1. And so the torque now has a fixed value which is equal to NIAB times nothing, NIAB, just simply NIAB. So this is the obviously the magnitude of it. The vector form always remains A with the A cross B. So this is now reduced with the or rather increased, or this is the maximum possible value of the torque that we can get, maximum value. So the case of any decrease in the value of torque has been done away with. That is completely discarded. Now with this arrangement, this is more or less the case of construction of the magnetic of the moving coil galvanometer placed with the coil, or the rectangular coil arrangement set over the cylindrical core placed between the cylindrical poles. So these are the cylindrical poles, So these cylinder and these cylindrical poles give out the radial magnetic field, which results in the maximum possible value of torque that we have just obtained. This setup can be placed in various arrangements as far as the use of the moving coil galvanometer is concerned. In case of a deadbeat galvanometer type, this arrangement is placed within a box, and a lamp and scale arrangement is placed in front of it, where we get the accurate measurement of the current at any given instant of time. Now, the string that is attached to this point that we see over here, that string will be having a restoring torque, or that string must be having some rigidity, and as a result of that, it will tend to restore the any deflection that occurs in the given coil. What essentially happens is that if this galvanometer, now we have to get back to the working of the galvanometer. So what does the galvanometer do? Well, it's simply the work of the galvanometer is that it detects the presence of current in a circuit. Now, if it is connected to a circuit, also we have the galvanometer to be converted into an ammeter and a voltmeter as well, but that is for later discussion. But as of now, first and foremost thing, the word galvanometer tells us that it detects the presence of current in a circuit, and if it is connected to a circuit carrying current, the current then flows through it, that is this current that flows through it and comes out. And as it comes out, because there is a flow of current in that coil placed between those cylindrical poles, a coupling force is established, which further gives a torque or produces a torque in that coil. And that torque, when it is connected, this device is further connected to a pointer, which gives the deflection either in one direction or the other, depending on the flow of current being in the clockwise or the counterclockwise sense. And thereafter, after showing the deflection and on removing the current from the circuit, the galvanometer is further brought back to its initial point, where a restoring torque acts on it, which is some constant times the angle theta through which it would have rotated. Now this angle theta, I would rather take it as some other angle, but theta, since we are done with the theta that was present in the cosine form at the top, we can afford to use another theta. So let's not confuse this theta with the previous one. I could have used alpha as well, but alpha again is the angle that it makes. Okay, let's use alpha because that's not mentioned in this page. So if it has rotated through an angle alpha, it is again brought back. No, it's the same angle theta. Wait, we'll keep it as theta. It's actually the theta that the twist goes through. So for a theta amount of twist, the restoring torque again brings back the coil through that same angle. So we have NIAB to be the torque that is acting to be equal to the restoring torque, and as a result of that, what we see is that the current is equal to C divided by NAB. Now all of these terms are constant. Obviously C is the constant for the given arrangement, given structure associated with the galvanometer, the string, that is the rigidity, and all of that, all of those parameters taken into account. NAB are going to be constant, they are not going to change. B is the magnetic field for those permanent magnets, even though they are cylindrical poles. N number of coils, they are not going to change. Area of cross section of the coil is also not going to change. So all of those terms being constant, we have the theta over here. So the current is proportional to theta. Therefore, it will have a greater deflection if we are having a greater amount of current flowing through the circuit. And that more or less explains even the faintest current that flows through the circuit can be detected by the galvanometer, thereby making its use worth uh, the arrangement, or worth the ambition that was there behind the construction of this galvanometer. So all that it has used is that it has used the concept of the torque acting on a rectangular coil, which we discussed in the previous video over here. And then further, the how it was used, well, it was connected to the circuit, and then a torque acted which was restored, and from that restoration what we can get is that the current is directly proportional to the angle theta. Now, if the galvanometer that we have, that we use, if it reacts in the smallest possible value of current that can flow, that defines its sensitivity. Now, considering these equations that we have obtained, if we just take another form of it, where we are considering the single twist, or the least deflection or unit possible deflection that can take place for the minimum value of current, that is what defines the current sensitivity. For a very small amount of current, if it is deflected through a unit point, then we define that term to be current sensitivity. So the minimum amount of current required to deflect the galvanometer through a unit deflection is what defines the current sensitivity, usually represented as SI, which gives the sensitivity. How much sensitive is the device to detect the presence of current? And conversely, if we are dealing with voltage, the minimum amount of voltage, then we must multiply a resistance term in the denominator, and then we have the resistance of the wire, of course. So we have, if we are multiplying it on the left hand side, we multiply it in the denominator of the right hand side as well, and that gives the voltage sensitivity, which also means that the minimum amount of voltage that can produce a deflection through a unit value. So that is what the voltage sensitivity is all about. So this is theta divided by IR, is nothing but the voltage, and that is equal to ST. So that's more or less the case with the moving coil galvanometer. Its arrangement, its working, the principle has been discussed already. We will be moving further into the topic where we will be discussing the case of the conversion of the galvanometer into a voltmeter as well as an ammeter. Now, as you can see that there's a pointer which is attached to that. You cannot see it over here, but as I mentioned, that the coil that rotates has a pointer attached to it, and by some arrangement, and as a result of that, what happens is that whenever there is a torque, whenever there is a current flowing in the circuit, a torque acts, and the pointer which is attached to the coil, it starts deflecting in one direction or the other, thereby showing the presence of current. And it is that usage of the pointer which gets deflected is what inspires the galvanometer to be further used into an ammeter as well as a voltmeter to determine the value of the current that is flowing in the circuit, or even the voltage or potential difference between any 2 points in the circuit. We had already discussed about the case of the potentiometer, which is again another device to determine the value of potential difference between any 2 points in the circuit. But this is the case where we are using the moving coil galvanometer instead of the direct approach of the potentiometer. So that will be in the upcoming videos. Till then, thank you for watching.